Good day, everyone. Welcome once again to our class in Math 1051, Engineering Calculus 1. So we'll continue our review on functions. So this is now part 8 of our whole topic, functions. So today we're going to focus our discussions on the transcendental functions. So we have here part of the transcendental functions is called exponential functions. So what are exponential functions? So we have here first the definition. Exponential functions for b greater than 0 and b not equal to 1 and all real numbers x. So we have here a definition that f of x is equal to b raised to the power x defines the base b exponential function. And we have here the properties of exponential functions. For real numbers a, b, m, and n with a, b greater than 0, so we have the following properties that if we have to multiply b raised to a power m by b raised to a power n, this is equivalent to b raised to a power m plus n. So it means that if you are multiplying the same or numbers of the same base, then we are just going to add their exponents. And another one is if you're going to divide a number with a base b by another number with a base b also, but their exponents are different, so we are going to subtract their exponent, but we write only one base, so b raised to upper m minus n. Another one is b raised to a power m. So this part here enclosed with a parenthesis, and the whole thing is raised to another power n. So this is equivalent to b raised to a power m times n. So it means that we just multiply the exponents. Another one is if you have the product of a and b, and the product is raised to a power n, so we can also rewrite this as a to the power n times b to the power n. Then if we have b raised to a power negative n, this is equivalent to 1 over b over 1 over b to the power n. And b divided by a, or the quantity b over a raised to a power negative n, is equivalent to a over b raised to a power positive n. Okay, a over b, the quantity raised to a power positive n. Alright, so these are the properties of exponential functions. And take note on the following definitions, the conditions here. Okay. For example, graph the following. So we're given here the function y equal to 2 to the x. So this is an example of exponential function. So graphing exponential functions with b greater than 1. Okay, so ang base natin is greater than 1. Okay, so we have the base equal to 2. So like in our previous discussions, one of the best way of graphing the function is to assume values for x and solve for the value of the function. In this case, we have y equal to 2x, so assume values for x and solve for y. So let us tabulate the values for x and solve for y. So we have this result. Okay, so we have b greater than 1. So let us see the result here. Okay, so if we plot these points, okay, so from this function y equal to 2 to the x, so when x is equal to minus 3, assuming or substituting the values of x equal to minus 3, so 2 to the minus 3, so using the property of the exponential functions, so we have 2 to the n or b to the n, that is equivalent to 1 over, sorry, from this we have a property that says b to the power negative n, so this is equivalent to 1 over b to the power positive n. So we're using this property. Okay, so because when you substitute the value for n here, which is minus 3, sorry, the values for x, which is minus 3, so 2 to the x or 2 to the minus 3, so using this property, then we have 1 over, because 2 to the you can rewrite this as 2 to the minus 3, so this is the same as 1 over 2 to the positive 3, and we know that 2 to the power 3 or exponent 3, that is equivalent to 8, so we have 1 over 8. Alright, and so on and so forth. So when you substitute 2, so this becomes 2 to the minus 2, or that is equivalent to 1/4, when x equal to minus 1, so that is 1/2, and we know that any number raised to a power 0, that is equivalent to 1. Okay, then for the positive values for x, so we have this result. Now when you plot this pair of values of x and y, the abscissa and ordinate, so we have it here. Alright, so for x equal to minus 3, so somewhere here, this is our minus 3. Alright, so our y is equal to 1 over 8. So what is 1 over 8? So when you get that value, so this is very close to 0. So 1 over 8 is equivalent to 0.125. Okay, so this value here, the height, the coordinate is 0.125. Okay, so 1 over 8 is equal to 125. Alright, and now in x equal to minus 2, so we have 1/4, so 0.25. Okay, so in x equal to minus 2, so this is 0.25 here for the y value. And when x equal to negative 1, so we have 1/2, so this one. So this is for x equal to minus 1. And when x equal to 0, so we have here 2 to the 0 is equal to 1. So this is 0, this is the origin. Origin is the intersection of x and y axis here. When x equal to 1, so 2 to the 1 is equal to 2. So when x equal to 1, so this is 1 here. Okay, so this is 1. And when x equal to 2, 2 to the 2 is equal to 4. So when x equal to 2, so you have, okay, so these are the coordinates of this point. When x equal to 3, 2 to the 3 is equal to 8. So when x equal to 3, so 2 to the 3 is 8. So these are the coordinates of this point. Okay, so that's for the exponential function. So another example here. In our first example, we have b greater than 1. Okay, so our base here is greater than 1. So for this next example, we have our b here is less than 1 but greater than 0. So graphing exponential functions with b greater than 0 but b less than 1. So we're given here the function y equal to 1 half raised to power x or exponent x. So this is our exponential function. Now again, tabulating the values for x and calculating the value for y. So we have the following result here. Okay, so I will not elaborate this one. It's just a simple substitution of the value of x to the given uh, equation. So in our do not be confused with this one. This is just the same as this. Okay, so you might be wondering why is it that we're having this. Okay, so any questions? So that is from the property. You have, so if you have all right, we are going to use the concept or the properties that if you have b or say a over b raised to a power n, so this is the same as a to the power n divided by b to the power n. Alright, so in this case we have 1 over 2 raised to a power x raised to a power x. So this is the same as 1 raised to a power x. So when I say power or exponent, they are just the same class. And 2 to the power x. So take note that any number, or sorry, 1 raised to any number that is always equal to 1. So this becomes 1 2 to the x, 1 raised to a power x. So x here can be any number. So 1 raised to any number that is always equal to 1. So we have 1 over 2 to the x. Okay, and this is equivalent to 2 to the power minus x. Alright, so that's why we have it here. So substituting the values for x, so we have the same assumptions here. Our x minus 3, minus 2, minus 1, 0, 1, 2, 3. And when you substitute the values for x, then you'll get the value for y. Okay, now plotting the points. So we have it here. Okay, so this is the result. So you have noticed that in our previous example, for b greater than 1, so our graph is, as you look at the first example, our b here is greater than 1, and this is our orientation of our graph. Okay, it's rising, uh, the direction is going to the right, rising exponentially to the right. But in our next example, for b less than 1 but b greater than 0, so we have the exponential graph on the opposite direction, rising on the opposite direction. Okay, next we have a very important properties of exponential functions. Now from the previous two examples, so these are the conclusion that we can draw from the results. So f of x equal to b raised to exponent or a power x, where b is greater than 0 and b not equal to 1. Okay, so properties, one-to-one function. So this is a one-to-one function. The domain of this function is x, that is element real numbers, and increasing if b is greater than 1. Alright, increasing if b greater than 1. And we have y intercept, that is at this point, coordinates 0, 1, and the range y is an element that is from 0 to infinity, excluding 0. Okay, uh, if if b is less than 1 but b is greater than 0, then it's rising to the left or decreasing, no? Decreasing. If you look at this, it's decreasing graph. All right, so it depends on the value of rx. So in this case we have the decreasing function if b is less than 1 and b greater than 0. And also asymptotic to the x-axis. What is x-axis? This one. This is equal to y equal to 0. So x-axis is the same as y equal to 0. So asymptotic. So what does it mean? It means that the graph will uh, come closer and closer to the x-axis, but it won't touch the x-axis. As we increase the value of x, or as we, in this case, as the value of x decreases, so the function will come closer and closer to the x-axis. Here, when we increase the value of x, now as the x is increasing, then we have the function come closer and closer to the x-axis, but it will not touch the x-axis. Okay, so we have to remember these very important properties of exponential functions. Now, for example, graph exponential functions using transformations. So we're given f of x equal to 2 to the exponent x minus 1, then plus 2. So we need to graph this using transformations. So we know already the original graph of the exponential functions using those properties. So now we are asked to graph this using transformation. So, well, you can still graph this using the conventional method of using the table, assume values for x and then solve for y. but there's a technique, to shorten the time of graphing it, if you know the rules in transformations. So we have here the, sorry, so if you graph this one, this is the graph of this given function. Okay, so uh, that can be done easily if you know this principle here, that uh, if you're given this function, so we have function plus 1 or equal to 3x plus 1. So the transformation is the curve moves up 1 unit, all right, and asymptote is y equal to 1. Asymptote is y equal to 1 for this value. In other words, you just need to look at the number after the first term, look at the next number, like this one, we have 2 to the power x minus 1 plus 2. So you look at this number here. So this is the number of units that the curve moves up. So in this case, if you compare this to the original exponential function, so this is shifted 2 units up. So this is our x-axis, this is our y-axis. Alright, so this is moved 2 units up. So we have 1, 2. Okay, so our asymptote here is y equal to 2. So this uh, indicates the number of units that the graph is shifted up. Now, if this is plus, if this is minus, then the graph will be shifted down. Now in the case of this, because originally we have 2 to the x, but now we have x minus 1. So it means that the graph also shifted to the right 1 unit. So take note for x, if this is minus, so the shift is going to the right. If this is plus, the shift is going to the left. Okay, so that is the transformation rule. Okay, so if you look at the graph, from this given, okay, so we know that from our reference x-axis, okay, this is our y-axis. So from this given, we know that the graph is shifted up 2 units. Okay, so you draw your asymptote, that is y equal to 2. From 0, this is our origin here. Okay, this is 0, 0. So this is our 0. So you move 2 units up, 1, 2. So this is where your asymptote will be. Alright, now the graph is shifted to the right 1 unit. Okay, so if you look at this, we know that the principle that we have y-intercept. Okay, so supposedly this is here, right, but it's shifted 1 unit. So this is our before the shift happens, this should be our y-intercept. Alright, so when it is shifted, so it is now in this coordinates 1 and 3. So from the x-axis, that is 1 unit, and then 1, 2, 3. Okay, so this is now the coordinate of this point. But if you move this back to the original position, for example, without this minus 1, without shifting this, so this point will come here. Okay, and your graph would look like something like this. Okay, so your asymptote, your intercept will be here. That would be 0 and 1. Of course, if you move this back also down without this 2. Okay, so from the original function f of x equal to b to the power x. Okay, so this is our original function, exponential function, f of x equal to b to the x. Now we have something added here. So this one, it means that the graph is shifted up 2 units, and if you have this minus 1, so it means that the graph shifted 1 unit to the right. So this is the standard graph of exponential function. It's just a matter of shifting it either to the right or left and up or down. So it depends on the given number here. Okay, and then we'll use these transformation rules. Okay, so if you have plus 1 here, you have asymptote equal to 1, but now it's 2, so your asymptote is equal to 2 in this example. Alright, I hope it's clear to everyone how to graph the functions, exponential function, using transformations. So you just need to remember this, that if you have this number, that is the asymptote. If this is plus, so it's going upward. How many units depends on this number. If this is negative, it's shifted down. How many units depends on this number also. And if you have here an exponent, x minus, so if that is minus, so it means you have to shift the graph to the right. If this is plus, then you have to shift the graph to the left. Okay, and then just use the same standard graph of exponential function. Uh, Standard graph of the exponential function, we have the y-intercept, that is equivalent to 0b. 0 yung x, you have b equal to 1. Okay, so that's it for exponential functions. Next, we have the what we call the natural exponential function. So what is this? This is the number e. Now for x greater than 0, x greater than 0, so as x approaches to infinity, so we have this 1 plus 1 over x raised to a power, meaning the quantity 1 plus 1 over x raised to a power x, this will approach to the number, we call it e, a natural exponential function. So in words, e is the number that this quantity 1 plus 1 over x raised to the power x approaches as x becomes infinitely large. So in other words, this quantity here, if you increase the value of x into a very huge number, then the value of this whole quantity, whole thing here, will approach to this number e. And we know that the number e is equivalent to, or approximately equal to, 2.7182818, and so on and so forth. Alright, so this is for the natural exponential function. For example, graph exponential functions using transformation. So we're given here the base this time class is equal to specific number, that is e. So graph f of x equal to e to the power x plus 1 minus 2. So using transformations of y equal to e to the x, so clearly states the transformation applied. Now again, we have to look at this number here and just think of it as use the uh, basic function as f of x. So we always have to refer to this basic function, b to the power x. Okay, so this is our basis. So b is any number. B can be less than 1 but greater than 0. Okay, so there are two conditions here, that our b is less than 1 Okay, and b is greater than 0, or the other one is for b greater than 1. Alright, so b greater than 1. Okay, let's check. So what I was saying is this one, these conditions here. B greater than 1, or b less than 1 but greater than 0. So we always have to refer this one. But e, what is e? Is 2.7182818. So which of these two? So it means that it belongs to this condition here, because 2 is 2.7182818. It is greater than 1. So we can say that the graph will look like this. Alright? So okay, so the graph will look like the one that is increasing to the right as we increase the value for x. Okay, so when you graph this, then we just use the transformation. So we have minus 2, so it means that from the original function it will shift down 2 units. Then this is plus, so it means it will be shifted 1 unit to the left. Okay, so 2 units down, so this is our x-axis, this is our y. Alright, so this is shifted 2 units down, so it means that our asymptote now is negative 2. Right, so this is our asymptote, which is y equal to minus 2, and shifted. So look at the point where this is our, there's a y-intercept. Okay, so since this is shifted down, the graph is shifted down, so look at the position of the intercept here, the y-intercept. So the coordinates now, the y-intercept from the original, because originally if this is the original y-axis, this is our 0 and 1, right? But this time, since this is shifted down 2 units and 1 unit left, so the coordinates of this point now is negative 1 and negative 1. Okay, so this is how to graph the function using the transformation technique. And you can check this one, you can tabulate values for x, so for f of x, and then do the same, no? In the previous example that we have, you just plot the points and you will really see this graph. But if you know the transformation technique, everything will be done faster. It's just a matter of knowing the basic concept. Like this one, e, we know the value of e, 2.7182818. So you know that e is greater than 1, and we have two conditions for b, less than 1 or greater than 1. So in this case, greater than 1, so it means that the graph will look like this standard graph of exponential function, but shifted down 2 units. This is plus, so shifted 1 unit to the left. Alright, so that's another example of exponential functions. Our last example is natural uh, function, exponential function. Next is logarithmic functions. So definitions, we have logarithmic functions for positive number x and b with b not equal to 1. So we have this uh, function y equal to log of x with base b if and only if x equal to b to the power y. So this is a very important concept, class. You need to remember this. So the function f of x equal to log of x base b, where the base b is a logarithmic function. Alright, so this is what we call logarithmic function with base b. And the expression log of x base b is simply called logarithm. Okay, so this is called logarithm and represent the exponent on b that yield x. Alright, so I hope you understand this principle, because otherwise you will not be able to solve problems that involves logarithmic functions, or if you're asked to graph the function, it's hard for us to graph if you don't understand this basic concept. Now we have here for the graph, so like the exponential functions, in logarithmic functions we have also these properties. So f of x equal to log of x with a base b, where b is greater than 0 and b not equal to 1. Greater than 0 but b not equal to 1. So this is a one-to-one function. The domain is an element in this interval 0 to infinity, excluding 0, increasing if b is greater than 1. Alright, so increasing if b greater than 1. Now, in exponential function, we have the y-intercept, but this time for logarithmic function, we have the x-intercept, which is located at the point with the coordinates 1, 0. 1 for x, 0 for y. Alright, so range, all real numbers. For the range, all real numbers. Decreasing if b is greater than 0 but less than 1. So it's just like the exponential function. But take note the condition here, b not equal to 1. Alright, so similar, no? Similar to exponential function. But this time the asymptote, as you look at this graph here, the asymptote is the y-axis, or that is the x equal to 0. Okay, so this is the asymptote, the broken line. This is the asymptote. So you should know what does it mean by asymptote? That is a line that the function get closer to but will never intersect. So in this case, we also have the asymptote, that is the same y-axis. So this is also the asymptote. Alright, so this graph, f of x is log of x base b, where b is greater than 1 here, or b is greater than 0 but less than 1, and b not equal to 1. So you have to take note the conditions. So in our examples later on, or example, you are asked to graph the function using transformation. So we just do the same as what we did in exponential functions. Right? So graph logarithmic functions using transformations. So this is the given logarithmic functions. F of x equal to log of x minus 3 base 2 and plus 1, using transformation of y equal to log of 2x, or log of x base 2. So not by simply plotting points. So perhaps you can use the plotting of points just to check our answer if it's correct. So clearly state what transformations are applied. Okay. So the graph of f is the same as that of y equal to log of x to the base 2. Okay, so what is that graph? So the base 2 meaning uh, our b is greater than. So what is b? Okay, so the basic concept here, we have b greater than 1. Okay, so it means that the graph will look like this. Alright, because our base is 2, so our graph will look like this. So we are going to use this concept, the intercept here. The intercept here is the coordinates b and 1. So the height is b, sorry, x is equal to b, that is the x-intercept. Okay, and we have 1. So this is our very important point that needs to be remembered, b and 1. Okay, so when you graph, so this is the original graph. All right. Okay, so this is our originally b1. Okay, b1. So it means our b, the height, and sorry, the b is the x intercept, and 1 is the height. Okay, now since this is plus 1, it means that originally this is our x and y axis. So this is plus 1, it means that the graph is shifted 1 unit up. Okay, and then since x here is minus 3, so it means that the graph is shifted to the right 3 units. Okay, so from the y-axis, the graph is shifted 3 units to the right, and we have 1 unit up. So the graph moves 1 unit upward. Okay, so it means this original point here, which is now this one, as after the shifting to the right 3 times. Okay, so with the same reference from here, you count 1, 2, 3. All right, so same here. So this is the original point. Okay, so you count 1, 2, 3. Okay, shifted 3 units to the right. 1, 2, 3. All right, then shifted 1 unit up. 1. Okay, so this is our new point, the reference. Okay, so this time you look at from this original uh, coordinate axis x and y. So if you look at this point now, so you have to count from here 1, 2, 3, 4. So the x value for this is 4, and the y value is, you count from the x-axis, so going up 1 unit. So that's why we have 4, 1. Then you just copy, copy the rest, because this is the for b greater than 0. For b greater than 0, sorry, for b greater than 1, so the graph, the logarithmic functions will look like this, originally like this one, with a asymptote. Okay, now what is the asymptote? So the asymptote is x equal to 3, so that is the distance from the y-axis towards this, or the number of units where the graph is shifted to the right. Okay, so this is the asymptote. So we have 1, 2, 3. So we have x equal to 3. This is our asymptote. Okay, do you have any question? So that's logarithmic functions. So another example. Okay, I see this is just the same. We still use this concept in transformation class. So just look at the number here, the plus or minus. Okay, so we still use this rule here. Now another function, we call it trigonometric functions. Um, for ECE and EE, so these are the functions that the mostly be exposed with. But for the civil engineering, perhaps you still have some applications that will use this concept. But anyway, I'll just brief you the basic of these functions. So we have here the sine functions. So if you look at the graph, so the sine will have this kind of period or a certain pattern that will occur in a certain period. So like this one, we have this is our 0, 90, 180, 270, 360 degrees, or that is equivalent to 2 pi radian. If you use radian, so we have here 2 pi radian. Okay, so note that the graph will start from at 0, 0. So meaning at the origin, if this is our x and y axis, so at the origin this is 0, and then it will rise up to this point at 90 degrees or quarter of the cycle. So we call it one cycle. Okay, so quarter of a cycle, it will reach a maximum of 1, right? And it will go down again and back to 0 at 180. So this is a half cycle. Okay, and then uh, going up but in the opposite direction, and it reached the maximum at 270 degrees, and that is for the negative. Okay, and then back to 0, and then this pattern will go on and on forever, no? As long as there's a source generating it that continues to generate it. So that's the sine function. And for the cosine function, it's just related to sine. Now we have cosine. So if you look at this, it also like a sine function, but you see at this point here, at the origin 0, 0. So this is the maximum of the function. No, at 0, 0, so the function is maximum at this point, and then it will become 0 at 90, and then go down to negative 1 at 180, and then back to 0 at 270, and then maximum again at 360. So again, this is one cycle. Alright, so that's for the basic cosine and sine functions. So there are a lot of tutorial that you can find from these sources, just to learn more details of our discussions about functions. Okay, so that's all for today, and hope to see you again in our next topic. So I'd like to end the review of functions up to this part of our discussions. So in our next discussion, that would be about limits. And there are a lot of applications of functions, and I think I have to discuss them later on in our topic on the applications. Okay, so thank you once again, and have a nice day to all of you. Bye bye.